Hello students, welcome to Inside Physics. I am Srinivas. Today we are going to discuss refraction of light at curved surfaces or spherical surfaces. See, refraction at spherical surface. Now in previous classes we have seen what is refraction of light and laws of refraction, Snell's law. So these details we have already discussed. Today our discussion is about the refraction of light at a spherical or curved surface. See, see the laws of refraction can also be applied to the spherical surface or curved surface as we have already applied to plane surfaces. Okay. See, now we have taken a curved surface. Okay. The refraction, that means the bending of light ray at the interface of two mediums. Bending means, see, because the velocity of light from one medium to another medium will change, so that the light ray will be changing its direction of its path in the medium when it is passing through one medium to another medium. So that happens, the change of direction of light ray happens because the velocity of light in different mediums is different. Okay, now we observe here what happens when we consider the refraction at a curved surface. See, generally when a light ray is getting refracted by entering into second medium from first medium, and it will be incidenting on a interface of the two mediums at a point, so that it will be refracting towards the second medium. Okay, so here if you observe, this is the object position and this is the point of incidence. Okay, the light ray is coming from the object and it is incidenting at the point N. After refraction at the interface, so that this is a curved surface, and this after refraction the image is formed at I. Okay, so both O and I, object and image, are here are considered as a point object and a point image. So the light rays are coming and it is making an image here after refraction. If you observe this dotted line, this is the line drawn from the center of curvature to the spherical surface. Any line drawn to the from the center of curvature to the spherical surface will be perpendicular to the curved surface. Okay, so this distance from center of curvature to the pole is considered as radius of curvature. Okay, this is the object distance, this is the image distance V from pole to I. Now the point of incidence here is considered as N, and this point at the pole is considered as M. Okay, so if you observe this diagram, the angle of incidence is I. So the angle of incidence is nothing but the angle between the incident ray and the perpendicular to the curved surface. So that this is the perpendicular and this is the incident ray. Here the angle is called angle of incidence, and if you observe this angle R, this is angle of refraction. So the angle of refraction is angle between the refracted ray, that means Ni, and between the perpendicular to the curved surface. Angle of refraction is angle between the refracted ray and the perpendicular to the curved surface. So this is angle of refraction. Now our aim is to here develop a relation between N1 refractive index of first medium, N2 and radius of curvature, image distance, object distance. So here we are going to derive a theory which will give us a relation between N1 and N2, radius of curvature, image distance and object distance. With that derivation or formula, we will observe the refraction at any curved surfaces the relation which we are going to derive will be applicable to all curved surfaces. Okay. So how to develop a theory or derive an equation for the refraction at curved surfaces? For that, we will take some symmetries using the properties of triangles. So here at the beginning, I have drawn a normal from point N to point M. This is the dotted line. If you observe, I have drawn a normal from N to M. So because the curved surface, the aperture of the curved surface is so small, that is the lenses or surface we take are very thin, so that the aperture of the curved surface is so small, so the lateral thickness will be considered as very small, and this nm is considered as a perpendicular to the principal axis. Okay, any small distance that may be deviated from this pole, we will ignore the distance and we will consider nm as a perpendicular to the principal axis, because the aperture of the curved surface is so small. Here, by the symmetry, if you observe triangle NOM, triangle NOM, we can write, if you consider this as angle theta, this one, we can write tan NOM is equal to this angle, that means opposite side by adjacent side, that means MN by OM, we can write like this. So if you consider as theta in terms of tan theta, and tan theta is equal to opposite side by adjacent side. If you observe the triangle NCM, again if you take theta here, and by tan theta we mean that perpendicular distance, that means opposite side by adjacent side, we can write tan N angle NCM is equal to Mn by MC. Okay. Again, if you observe the triangle NIM, NIM, we can take theta here, and from tan theta we mean that opposite side by adjacent side. So here we can write tan angle NIM is equal to opposite distance Mn by adjacent side, that is Mi. So these are the angles we are taking from this diagram and with the help of properties of triangles. So if you observe these three equations, we can write for small angles, if theta is very small, we can ignore tan and we can write angle NOM is equal to Mn by OM. We know that for very small angles we can write sin theta is equal to theta, or tan theta is equal to theta. We can take sin theta as theta for very small angles. This implies again angle NCM is equal to Mn upon MC. This implies again angle NIM is equal to Mn upon Mi. Okay. These are the distances we have taken from this diagram. Okay. So if you observe, the angle of incidence is an exterior angle from for triangle NOC. See, if you observe this diagram, angle of incidence I is an exterior angle for this triangle NOC, right? If any angle is an exterior angle for the triangle, the exterior angle is equal to sum of the angles that are opposite to the exterior angle. See, we can write this angle is equal to angle NOM plus angle NCM, right? Angle of incidence is an exterior angle for the triangle NOC. So that we can write this angle I is equal to sum of NOM and NCM. So here we write angle I, angle of incidence, is equal to sum of NOM plus NCM. Okay. So here what is NOM? MN by OM plus what is NCM? MN by MC. Okay. Now if you observe again here the angle of refraction. Angle of refraction will be from this triangle NIM and NCM. Angle of refraction can be obtained by subtracting angle NIM from angle NCM, right? Angle of refraction can be obtained by subtracting angle NIM from angle NCM. So now we can write, so R, angle of refraction is equal to angle NCM minus angle NIM. Okay. So what is angle NCM? Here MN by MC, angle NCM. What is angle NIM? That means MN by MI. Okay. NOM, MN by OM plus NCM, MN by MC. So angle of incidence and angle of refraction are taken in this form. Okay. Now we know from Snell's law. See, Snell's law says sin I by sin R is equal to N2 by N1. That is, we can also write it as N21. Okay. Snell's law says sin I by sin R is equal to a constant called refractive index of second medium by refractive index of first medium. So from this equation we can write N1 sin, see, N1 sin I is equal to N2 sin R. From this we can write N1 sin I is equal to N2 sin R. See, again for some small angles, if angle theta is very small, we can write sin I is equal to I and sin R is equal to R as per these two equations. So here this becomes N1 I is equal to N2 R. See, N1, N2 are the refractive indices of the first medium and the second medium. See, this is, if you consider N1 as air or vacuum, the light ray, that means from the object, the incident ray is entering into the second medium, that is into the curved surface. Now we consider this as second medium, this as first medium. So N2 is the refractive index of the second medium. So N1I is equal to N2R. Now if you substitute I and R values, so this is I, this is R, in this we can write, see, N1 into I Mn by OM plus Mn by MC is equal to N2 into R. What is R here? Mn by MC minus Mn by Mi. Okay. So this is what we got, n1 into I, n2 into R. This is I, this is R. We have substituted in this equation, we got in this form. Okay. So if you observe this equation, we can take Mn from LHS and RHS, we can take the Mn as a common factor and we can cancel on both sides. Okay. So see, this will become N1 by OM plus N1 into 1 by OM plus 1 by MC is equal to N2 into 1 by MC minus 1 by MI. So here I have taken Mn on both sides as a common factor and I have cancelled on both on LHS and RHS, so that it has become like this. So now we can write N1 by OM plus N1 by MC is equal to N2 by MC minus N2 by MI. Okay. See, if you observe this equation, we can take the MC terms on one side and these two terms onto another side, right? So by this we can write N1 by OM plus this. I will take the term of this one to the left hand side. Mi is equal to N2 by MC minus N1 by MC. Okay. See, this is the equation we got from the above one. So if you observe this right hand side, I can write this 1 by MC, I can take the common factor and I can write in the form of N1 by OM plus N2 by MI is equal to, so N2 minus N1 by MC. Okay. So what is OM? The distance OM here from the diagram. OM is nothing but object distance. OM is equal to U. And MI, what is MI? MI is nothing but image distance. Image distance V. So MC, if you observe MC, this is the distance from pole to center of curvature is nothing but radius of curvature. Okay. So this is OM is object distance, MI is image distance and this MC is radius of curvature. Okay. So now this is the relation we have got when we have developed a theory for the refraction at curved surfaces. So this equation can be applicable to all curved surfaces. So now we can write this one as N1 by object distance. Can we write object distance plus N2 by image distance is equal to N2 minus N1 by radius of curvature. See, N1 by OM is object distance, OD means object distance, N2 by ID image distance, N2 minus N1 by R. So what is object distance here? U. See, with the sign convention we can write object distance as minus U, because Sign convention says the distance is measured from the pole to the object and it is opposite to the direction of incident light ray. So here with this we can write n1 by minus u plus n2 by mi is nothing but v. So v is measured from pole to the image and it is in the direction of the incident light ray. So it can be taken as positive. Okay. So radius of curvature is also positive from pole to the center we measure. So it is in the direction of incident light ray. So we can write this equation n2 minus n1 by r. So if you transform these, okay. So this is the relation between n1, n2 object distance, image distance and radius of curvature. So here what we have done is we have developed a theory to study the refraction at any curved or spherical surfaces. Okay. So with this we can also develop a formula for a lens which we will going to derive in the next class. So that relation is called lens maker formula, and a lens is a combination of two curved surfaces, okay, having two radius of curvature on both sides. So for now we are going to end this class, and in the next session we will derive the lens maker formula and lens formula. Okay.